All right, welcome to 4.3, the first derivative test. The first derivative test is linked to 4.1 and 4.2, so a lot of what we're doing within 4.3 is going to be reiterating the concept. And I'm going to explain it in this little kind of table, and this is all in your notes. It says that if f prime of x changes from positive to negative at c, and it should say kind of over c, I think, then it says that f has a local maximum at c. Now, what that looks like graphically for number one here is that if f prime of x is positive, the function is increasing, and then at c, it changes to decreasing. Well, if we thought about a graph, that right there would be a maximum point because it's the highest relative to others. For number two, if we're changing from negative to positive, similar situation, sorry, it's decreasing and then it's increasing. This right here would be the c value, so that would be a minimum. And then the last case is that if f prime of x does not change sign at c, this has no minimum or maximum. I think the easiest way to show that is if we looked at y equals x cubed, y prime would be 3x squared. The critical number is x equals 0, but if I graph that function, y equals x cubed is always increasing. This point right here, which is at x equals 0, is neither a minimum or a maximum. And the derivative has a constant sign. It's always positive for y equals x cubed. Now, I think drawing that out is really, really helpful. We're going to look at basically the same with one extra situation. I like having the graph here because it really shows us that f prime, if we identify, and I'll do this all the way down, that this dotted line for all of these examples is when x is equal to c. That's our critical number. So looking at the slope of the graph, which tells us the sign of the derivative, for example one, it is increasing here and decreasing there. That means to the left of c, f prime of x is positive. To the right of c, f prime of x is negative. That means that f prime of x, or f of x I should say, is going to have a maximum at x is equal to c. And if you look at that graph, it does correspond with that maximum appearance. Okay, for the second row of this table, to the left of the number it's negative, to the right of the number is positive, and that's dealing with the slope of f of x. I'm just going to put f of x up here, which means that we would have a minimum at x equals c. For these other examples, this is that y equals x cubed. It's positive everywhere, so this would have neither. Right? That may be an x-intercept or whatever it is, but it is not a critical number yielding a max or a min. And then for the last example, this could be y equals negative x cubed. That function is always decreasing, so it is neither. And I shouldn't say always decreasing. It could still have a slope of 0. It does at this point. But because it's not, the derivative isn't changing signs, the function does not have a maximum or a minimum. Now, what this looks like is much more similar to the questions we've done in the past. To find the local max and minimum, we are still doing the same concept we did before. We're going to take f of x, determine what f prime of x is, so that's going to be 3x squared minus 3, and then we're going to determine what values of x make f prime of x equal to 0. Well, to do that, we solve 3x squared minus 3 is equal to 0. I can factor a 3 out, which leaves me with the difference of squares. So that's 3 times x minus 1 times x plus 1. So my critical numbers are going to be x equals 1 and negative 1. From that information, we can generate our sign chart. And this is just a useful tool for us to determine when the derivative is positive or negative. So I'm going to put in the factors of my derivative. There's 3. 3, x minus 1, x plus 1, and then we're going to look at the sign of the derivative at the end. The way that we break that number line apart is with our critical numbers. One of my critical numbers is at negative 1. The other critical number is at positive 1. I really do recommend writing the intervals in. This interval is from negative infinity to negative 1, from negative 1 to positive 1, and from 1 to positive infinity. And really all that's left is to determine the signs on these factors. Now, because 3 is always positive, I truly didn't need to include it. Multiplying by a positive number never changes the sign, but just for consistency, I'm going to include it in most cases. But 3 is always positive. Doesn't matter what the interval is. X minus 1, on the other hand, is negative from negative infinity to negative 1. It's also negative from negative 1 to positive 1. Remember that you can pick a number. So I could, use, let's just say x equals negative 10 here, x equals 0 here, and x equals positive 10 there. If I plug those numbers into the factor, that will tell me if it's positive or negative. Negative 10 minus 1 is negative 11. so that checks out. 0 minus 1 is negative 1. And then finally 10 minus 1 is positive 9. Okay, we'll do that same concept for the third factor. Negative 10 plus 1 is negative, 0 plus 1 is positive, and 10 plus 1 is positive as well. All right, for this first interval, a positive times a negative is a positive, so the function is increasing. I'm just going to write f of x down there. We'll talk about the shape of f of x. Here it would be negative, so the function is decreasing, and then finally in the last column will be positive again, so the function is increasing. Now, looking, and that's why I like writing or drawing, I suppose, the shape of f of x, is it does help quite a bit, I think, to identify that at negative 1, we have a maximum. So it is a maximum at x equals 1. We could determine where that is. The original function evaluated at 1, or sorry, negative 1. I had it right in the table. I scrolled down too far, I suppose. Let me erase that. So the maximum occurs at x equals negative 1. And the function f evaluated at negative 1 gives me 3. And that is going to be a local max. We would have to look more at the graph. This particular graph won't have any absolutes because y equals x cubed, the cubic polynomial, goes to positive and negative infinity. So there is no absolute highest or absolute lowest point. But there is a local max and a local min. This shows that we have a minimum at x equals 1 and the function evaluated at 1 is equal to negative 1, and that would be our local minimum. I really do think it's beneficial to draw that shape of f of x in there. That helps to identify when we would be switching from increasing to decreasing, or decreasing to increasing. All right, we'll do another one, and then I think I'll split this lesson here. Really, the hassle is sometimes the shape of the graph, but the more complex the graph, the more complex the derivative. But you have been, trained might not be the right word, but you've done a lot of work in factoring higher than quadratics, and this kind of coming home to roost, I suppose. So f prime of x is 4x cubed minus 12x squared minus 16x. We are going to solve when f prime of x is equal to 0. 4x cubed minus 12x squared minus 16x is equal to 0. We need to do some factoring here. I can factor a 4x out. That leaves me with x squared minus 3x minus 4. Then I can further factor that quadratic. So my factors are 4x times x minus 4 times x plus 1, which means we have 3 critical numbers. My critical numbers in order are x equals 0, x equals 4, and x equals negative 1. When I say in order, I just mean that these are corresponding to each of the factors in my derivative. Okay, with those numbers, we can generate our sign chart. And I shouldn't just say with those numbers and factors, our sign chart. So I'm going to use the same concept or the same technique I've been using for the last couple lessons here. I'm going to write the factors as rows. So 4x, x minus 4, and then x plus 1. And then similar to that first example I did, we are going to look at the sign on f prime of x and then the shape of f of x. And that'll help us to determine these kind of local maxes and mins and so on. So to do this, what I'm going to do now is basically take my critical numbers and break apart the number line. So negative 1 is here, 0 is here, and then finally positive 4 is the far right there. Again, writing the intervals is an advantage. So negative infinity to negative 1, negative 1 to 0, 0 to 4, and 4 to infinity. You can pick a number within there, but as you do more and more of these, you are going to get better at identifying the signs. A negative times 4 is a negative, so this will be negative in both of those locations. And then when x is positive, 4x will be positive as well. X minus 4. Again, pick a number if you're struggling. X equals negative 5 would give me a negative. Negative 0.5 minus 4 is still negative. Anything between 0 to 4 minus 4 is still negative. But finally, from 4 to infinity, x minus 4 would be positive. X plus 1 is going to be negative here, positive here, and then positive for the rest, which means that f prime of x is negative from negative infinity to negative 1, so it's decreasing. It's positive from negative 1 to 0, so it's increasing. It's negative from 0 to 4, so it's decreasing. And finally, it's positive from 4 to infinity, so it's increasing. Now, this function is, relatively complex. And I lost my little grid there, but I am going to draw it here. This is a quartic, and it looks something like this. Roughly. Again, that's not a perfect graph. And we do see that we have 1, 2, 3 local mins or local maxes, which corresponds with the critical numbers of our derivative and our sign chart. So I'm going to grab that information from the sign chart. We should have local mins, at least local mins. We're going to talk about how we know one is something different. It's going to be at these two locations when the graph is changing from decreasing to increasing. So one of those is going to be at x equals, that would be the first, so that's -1. The other is going to occur at x equals 4. We should find out what the function is there. It is function g, which is a slight difference here. So g at -1 is -4, and g at 4 is -129. Now, looking at that graph, and hopefully you can look up at it, this is the lowest point. So this is actually an absolute min. We'll talk a little bit more about that in the last example, but this would give me a local min, and then 4, -129 is the absolute lowest point on this graph. Local maxes, there is only one. That's going to be when x is equal to 0. And if we evaluate function g at 0, we get positive, or sorry, not positive, -1. And so that would be a local min. And you know what? I made a, sorry, what did I do here? Oh, that should be a local max. My bad. I had it right, and I thought I made a mistake there. So g at 0 equals -1 would be our local max. Identifying points like that, if you remember way back in 20-1, you talked about how to find a vertex on a parabola. This would be a good way of doing that because we could take the derivative. It would be much simpler than completing the square.